Hello and welcome to lecture 57. We are discussing about the Turboshaft engine. In last lecture, we were discussing about the type or we can say configurations possible for the Turboshaft engine, where we have discussed about the single spool Turboshaft engine with recuperator, booster compressor on HP spool or say LP spool, double booster kind of configuration on HP spool or LP spool. Here in this case, if we look at the diagram, we have realized, suppose if we consider this as a configuration, we can say it is a 2 spool configuration. Sometimes people they used to say single spool configuration also, where HP turbine, that is what is connected with the compressor, and we have additional turbine, that is what we have defined as a free turbine or power turbine. The purpose of this turbine is to generate the shaft power. So, we have discussed all this in last lecture. Then we have analyzed the thermodynamic cycle for this turboshaft engine, and we have solved a numerical, that is what will be building the confidence in order to understand how do we go with the cycle analysis for turboshaft engine. Now, let us move towards the next approach. Before going into the next approach, we must realize we have discussed about say initially with the turbojet engine, where we have discussed single spool configuration, then we have continued discussion with say 2 spool engine, then we have discussed about say operation of afterburner, non operation of afterburner for the turbojet engine. Then we have discussed 8 different configuration for the turbofan engine. Then we started discussing say configuration which are related with the say turboprop engine, and in this week we are discussing about the turboshaft engine. This turboshaft engine we have discussed, it has main application for the helicopter engines. Now, here in this case, suppose if we configure our engine or future engine, where we would like to have say flying capacity or the maximum possible speed available or achievable, that is what is equivalent to say turbofan engine, and efficiency we are expecting as a turboprop engine. So, we will be discussing about the next kind of configuration or the future configuration or say already existing few engines with this kind of configuration, that is what we say in terms of propane engine. So, here in this case if we look at carefully, the construction is similar in the sense, but in this case we are having say free turbine or power turbine which is used to rotate say the shaft. Here in this configuration if we look at carefully, we are having 2 spool configuration, that is what is with the core engine, and on later part we are having say turbine. This turbine, it may be of contra rotating configuration or may be contra rotating configuration with say gearbox kind of configuration. So, here in this case if we look at carefully, we are having 2 prop fans, they are connected on the rear side with the free turbine, and these free turbines they are rotating in counterclockwise direction. So, this if you recall, we have discussed this kind of construction in week 9, where we have discussed about G36 engine. So, history and background we have already discussed with. So, let us try to understand, let us try to recall what all we have discussed and how do we analyze this kind of engine for say thermodynamic analysis, because we cannot miss the upcoming engine, that is what is of great use. Let us see. So, here in this case if you recall, we have discussed this is NASA GE36 engine, where we are having say 2 propeller fans, they are rotating on counterclockwise direction and they are placed on the rear side of the engine. And here if we look at carefully, this is what is our core engine. We have discussed about the puller kind of configuration and pusher kind of configuration. If you recall, say for turboprop engine, if our propeller is placed in front of our intake, then we can say it is a puller kind of configuration. When it is placed on the rear side of your intake, then it is called say pusher kind of configuration. So, here in this case we are having front rotor which is having 10 blades and the rear rotor it is having 9 blades. And in this case the rotation, opposite direction rotation, that is what was not been achieved, but with the gearbox kind of configuration. So, it is a non-geared kind of configuration. So, during 80s there was a price rise, it rose like anything, and that is what has attracted the attention of engine manufacturing companies to move towards the fuel economic engines. If you recall, in week 9 we have discussed this kind of open configuration, they are best performing in terms of fuel burn, as well as that is also helping us in order to reduce the carbon footprint, and that is the reason why for the future engines this has a attraction. Parallel to G36, Pratt and Whitney and Allison, they have developed the engine, it is 578DX. In terms of construction, if we look at, that is also having the pusher kind of configuration. In this they have 6 front blade and 6 rear blade, but the rotation, a counter rotating configuration, that is being configured by using gearbox. So, this gearbox, that is what is helping the rear rotor to rotate in counterclockwise direction. So, both the engines, they were being tested during 80s by McDouglas MD-80, and that is what was a major attraction, because Boeing was planning to replace 727 by 7J7, and that is the reason why they have installed these engines on the fuselage part, on the rear part mainly. Now, in collaboration with GE, Safran was working on the development of different kind of engine configuration, as we have discussed. One of them, it is say CFM56, and during that time only they have developed the best engine configuration. Later on, based on the information available by GE36, they started working on. The difference here in terms of GE36 and this SNECMA Safran open rotor configuration is they are having say counter rotating configuration they have achieved by placing the gearbox. And the major challenge for this kind of configuration those days, it was with the higher noise, and Safran that has come up with the solution with reduction of the noise, and that is what is a future upcoming engine. Parallelly in Russia, Ukraine and Russia, they have developed combinedly in terms of the configuration. Here if we look at, this is what is a puller kind of configuration. The engine, it is tagged as a D27 that was used for Antino 70, where we are having a different kind of propeller configuration, prop fan configuration, they are placed in front of the intake. Now, with this background, if we move ahead with the current ongoing research and what all they have done in past 5 years, if we look at, SNECMA has explored different kind of configuration. One of them, it is a direct drive kind of configuration. Second configuration in which the rear fan, that is what is with say rear configuration, with the rear fan it is rotated with the gearbox. Here this is what is a front configuration, that means this is what is a puller kind of configuration with the gearbox. One more configuration they have explored, that is what is with the single rotor, but that rotor is the geared one. Here if we look at, this is representing clearly the cut section of the Safran engine, where we can clearly see this rotor, it is rotating in clockwise direction, and the other rotor it will be rotating in counterclockwise direction by using the gearbox. Now, this is what is giving the overall picture in terms of how the future engine will be. So, here if we look at, this is representing CFM 56. Then later on we have realized by increasing the bypass ratio, it is possible to improve the propulsive efficiency, and that is what is helping in terms of improving the fuel economy and overall efficiency. Later part, if we look at this engine, that is what is representing the SNECMA coming engine. But here if we compare all these engines, we must realize the height or say the blade height of this engine or the diameter of this engine is very large, and that is where the challenges are. and in different configuration they have tested with the performance at Mach 0.78. As we have discussed, this engine, it's a combination of prop engine and the turbofan engine, and the high flight speed in the range of 0.6 to 0.8, that's what is a requirement for them. Okay. Now let's look at, as we have discussed, the next challenging part, that's what is to move from high bypass ratio to counter rotating configuration, where we can say very high bypass ratio engine, and the current train, that's what is with say ultra high bypass ratio engine, where the bypass ratio will be in the range of 45. And here if we look at the major concern, major challenge, it is to reduce the noise as well as to improve the fuel economy. Okay. Now let's try to look at, you will be having confusion saying like, sir, what is the difference between this turboprop engine and prop fan engine? So let's try to understand the case. If we are talking about the turboprop engine, we have discussed the number of blades, propeller blades, they are in the range of 3 to 6, where for prop fan what all we have discussed, they are having number of blades which are ranging from 8 to 12. So we are having more number of blades. Okay. Next configuration, it is say diameter. If we look at the turboprop engine, the propeller diameter is larger. If we are comparing with say turboprop engine, for the propeller fan, the diameter is smaller. The power per square meter diameter is smaller for turboprop engine. For the propeller engine or prop fan engine, that's what is very large. Same way, if we look at the blade shape, say propellers are of nearly straight blades, and we have seen for the prop fans they are of say swept or maybe scimitar like profile. They are having different kind of configuration, because that need to satisfy the requirement of aerodynamic performance, as well as the noise is a major issue with that kind of configuration. If we recall, for turboprop engine also noise is a issue, and that is the reason why current propellers, if we look at, they are having swept kind of configuration. So if we compare the maximum thickness, this say propellers are thicker one and prop fans are little thinner. And if we configure say tip speed, then for the turboprop engine we do not want our flow to go supersonic or transonic near the tip region. So this tip speed, it is subsonic, and for prop fan we can go in supersonic range also. If we configure the bypass ratio, then for turboprop engine we have bypass ratio in the range of 50s, and for prop fan it is more than 25. You can say the comparison of this prop fan is more with the turbofan engine. In terms of propulsive efficiency, for turboprop engine the efficiency is higher, but even higher efficiency can be achieved with the prop fan engine. So equivalent specific fuel consumption, that is what is lower for the prop fan engine, it is in the range of 0.17, and flying Mach number, that is what is a major attraction for the prop fan engine. We can say it is permitting us to fly at higher altitude, at that cruise speed may be in the range of 11,000 meter. That is what is a future requirement in terms of flying altitude as well as Mach number, to achieve different benefits what all we are discussing for all these engine configurations. So in overall, if we look at, there is no concern, there is no straightway relation between turboprop engine and prop fan engine. So you should not get confused with this configuration. Okay. Now let us try to understand this engine. If we look at this engine carefully, then the initial part of this engine, it is similar to what all we have discussed for Turboshaft engine. Okay. And next portion what we have is our free turbine kind of configuration. Now here in this case, how the flow exit will be happening. So if you recall, for turboshaft engine, as we have discussed, major concern is with the shaft power generation. But for this kind of configuration, if we look at, we will be having the exhaust nozzle also. So this exhaust nozzle, that is what is putting additional benefit in terms of thrust generation. Okay. These engines are conventionally in the range of say 2 spool or the 3 spool kind of configuration. So, we should not get confused with the turboprop engine and prop fan engine. Now, let us try to understand the stations. So, here infinity I say it is a free stream condition, 2 it is at the exit of the intake or the entry of the compressor, 2 to 3 that is what is representing the LP compressor, 3 to 4 which is representing say HP compressor, then we have 4 to 5 as a combustion chamber, 5 to 6 that is what is representing the HP turbine, 6 to 7 it is representing our LP turbine, and let us say like 10 to 11 that is what is representing our prop fan configuration. Here in this case from 8 to 9 that is what is representing the engine exhaust. Similarly, this 12 configuration we say it is a free stream condition or free exit condition. So, now let us try to understand how do we analyze this kind of engines. Okay. So, very first component let us take is say intake. For the intake actual process that is what can be represented from process say infinity to P02. Here in this case again we have our intake, and for that intake the diffuser efficiency that must be known to us, or maybe we need to assume. Maybe other parameter pressure recovery factor that also can be used for this purpose. Once we have this information, we can calculate what will be the total pressure at the exit of our intake. Here in this case, if we are looking for the exit temperature, that is what will be the entry temperature for the compressor. These two parameters can be calculated based on this diffuser efficiency configuration. We need to recall here when we say it is a ground condition, our M infinity that is what will be 0, and when we are having flying condition this M infinity we need to consider the flight velocity. Okay. So, this will be giving us the idea about the calculation of exit pressure and exit temperature from the intake. Now, let us take the next process that is what is say our HP compressor. So, for HP compressor we have information about the pressure ratio. Based on that we can calculate what will be the exit pressure from the LP compressor. We also know the efficiency. We have two efficiencies as we have discussed earlier also. If we are having number of stages, then we can configure that as a polytropic efficiency, or maybe we need to configure that as a adiabatic or isentropic efficiency. So, based on that we can calculate what will be the exit temperature from our LP compressor. So, we have now information about exit pressure and exit temperature from the LP compressor. Now, let us look at the next component we have, it is our HP compressor, and for this HP compressor we may be having information about the pressure ratio. So, based on that pressure ratio we can calculate what will be the exit pressure or maybe entry pressure for the combustion chamber. We have the equation of say isentropic efficiency, that is what is correlating the pressure ratio and the polytropic efficiency. Based on that we can calculate what will be the exit pressure and exit temperature from this HP compressor. So, if we look at this, all things seems to be similar what all we have discussed for almost all cycles, but be careful, it seems straightforward, but the thing is the selection of this pressure ratio, that is what is playing major role, very important role. So, when we have started our cycle analysis for turbojet engine, where we have discussed what will be the effect of say different parameters on the performance of the engine. So, you need to recall those terminologies and you need to decide with what will be the pressure ratio and what need to be the efficiency, that is what we need to assume. The assumption does not mean that you assume the compressor efficiency 0.98%, it should be valid efficiency number and it should be achievable. Okay. Now, let us look at the next component we have, that is what is combustion chamber, and for this combustion chamber we will be having say actual pressure at the exit of combustion chamber, that is what will be lower than the say entry pressure of the combustion chamber, and that is what we are correlating by this delta P. Now, in order to understand what will be the fuel or amount of fuel, that is what is required to raise the temperature to T05, we need to go with our say energy balance equation. Here in this case, my entry configuration, we can say it is m dot infinity into H04, and exit configuration we can say m dot H phi and H05. Here this is what is representing m dot into QR and what will be my burner efficiency. So, if we will be writing the energy balance, we will be able to calculate what is the amount of fuel, that is what need to be added with. Do not get confused in terms of M infinity and M core. Suppose if I consider this is the engine, for that we can straightway write down M core. Okay. Now, based on this we can calculate what will be the fuel air ratio, that is what is required, or amount of fuel required to be added in order to raise the temperature to T05. Okay. Now, let us move towards the next configuration, where we are having our HP turbine. We know this HP turbine mainly been used to rotate the HP compressor. So, in order to calculate what will be the temperature at the exit of HP turbine, we need to write down the work balance equation. Let us put the work balance equation here. In this case, this is representing my compressor work, it is m dot CPC T04 minus T03, and this is representing my turbine work, that is what is m dot core 1 plus F Cp T05 minus T06. Based on that, we can calculate what will be the exit temperature from our HP turbine. Now, our requirement also is to calculate what will be the exit pressure from the HP turbine. So, that exit pressure we can correlate by using say isentropic correlation. If we will be simplifying this thing, then we will be having the pressure ratio in terms of efficiency and the temperatures. So, if we are putting those numbers, we can calculate what will be the outlet pressure and outlet temperature from the HP turbine. Okay. Now, the change, that is what will be coming with. So, let us try to understand. Here in this case, if we configure, we are having say LP compressor, that is what will be rotated by say LP turbine, then we can write down our work balance in terms of say this equation. Remember, if there is a number which is given, we say mechanical efficiency, then this formulation, that is what will be different. Now, I am sure after 10 weeks you must be clear with all those things. So, no need to repeat it again here. So, let us put this equation. So, on left hand side what we have written, that is what is my LP compressor work, and on right hand side I am having say LP turbine work. Okay. So, if we will be putting this equation, we will be able to calculate what will be the total exit temperature from the LP turbine. We can calculate what will be the pressure at the exit of the LP turbine based on the pressure ratio equation, that is what is correlated in terms of temperature and our isentropic efficiency. Okay. By this way we can calculate, or we can locate our point 7. At point 7 we can calculate what will be the total pressure and total temperature. Now, let us move towards the next component. Here in this case, let us focus first on say 10 to 11. So, that is what is representing say the station for unducted fan. Okay. So, at the entry here at station 10, we have our air, that is what is ingesting or it is striking on the front rotor. For that we can say my temperature we can calculate based on my Mach number, considering this as a isentropic flow, and for the pressure also we can calculate based on the Mach number. So, we can calculate what will be the temperature and what will be the pressure at the entry of my fan, prop fan. Okay. Now, let us try to understand here, in order to calculate the parameters at the exit of this prop fan, we have our information about the pressure ratio. Based on that pressure ratio, we can calculate what will be the outlet pressure from this prop fan. Similarly, since we have information about the pressure ratio as well as efficiency, we can calculate what will be the exit temperature from this prop fan. So, be careful here. Here in this case we are discussing about say contra-rotating unducted fan. Similarly, suppose say if I will be having only one fan or one prop fan, single rotor, then also this correlation that is what will remain same. So, if you recall, we have discussed about the RISE program, where we are having say rotor that will be followed by the stator blade, and those rotor we have discussed that is what is having pitch control configuration. Even stator also can be pitch as per the requirement. So, for that also this formulation that is what will remain same. So, do not get confused here. So, here in this case if we look at this process is represented from P infinity to 10, and then after we will be having rise of pressure, that is what we have kept as say from point 10 to 11. Okay. Now, let us try to understand the later part, because we are more interested in what is happening at the exhaust, because this exhaust we are correlating in terms of thrust, and thrust we know that is what we are correlating with the momentum thrust, momentum drag as well as pressure thrust. So, in order to calculate that momentum thrust, we need to have what will be the exit velocity, and in order to have that exit velocity configuration, we must know what will be the static temperature at the exit. Now, in order to calculate that static temperature, we can write down the ratio of the temperature by this formula. Now, this is what will be giving me the number in terms of what will be the exit velocity from the ducted fan. So, now we have our stations 10 and we can calculate what will be the exit velocity from the unducted fan. Now, let us try to understand what is happening here inside, because that is also of our interest. What is the exit station from my LP turbine is say station 7, and exit of my free stream turbine or say free turbine or power turbine, that is what is say station 8, okay, and station 9 that is what is representing my nozzle. So, if you recall, we have discussed this kind of configuration when we were discussing about say turboprop engine. Here in this case we do not have information in terms of say propeller configuration. So, if you recall, we have discussed about ideal enthalpy, then we have introduced the parameter that is what we say in terms of say alpha, say this alpha we have defined as say power factor, okay, power split factor or split power factor, that is what we are writing in terms of alpha delta H 1 minus alpha delta H. So, this is what is our requirement. So, we need to calculate very first thing, that is what is our delta H. So, let us try to understand here. Here in this case we will be configuring the process, that is what is say isentropic process. That process we are writing in terms of 7 to 9 S. So, from that we can calculate what will be the exit condition. Okay. Now, what we have information is in terms of work developed by the free turbine, that is what we are correlating in terms of say efficiency of the free turbine into alpha into delta H. This delta H we are writing in terms of 70 T07 minus T9S, and if we have this information, from that we can calculate the efficiency point. This efficiency, that is what will be helping us to locate the point 8 or say 0.8 and 0.8 S. So, here in this case, based on this we can calculate what will be my 0.8 S. Okay. Now, what is my next configuration is we need to calculate what will be the outlet pressure from the free turbine. Now, that we can write down in this formula, because we have our information in terms of isentropic expansion from 7 to 8 S. We have calculated the temperature at the station 8 S. We can straightway calculate what will be our say the pressure at the exit of the free turbine. Now, we need to check with the next component. The next component we have is say 8 to 9, that is what is representing our nozzle, and for that nozzle we need to calculate first whether our nozzle is choked or unchoked configuration, and for that we will be calculating our critical pressure ratio. Based on that critical pressure ratio, we can calculate what will be the outlet pressure. Okay. Now, this outlet pressure once we have, we can calculate what will be the exit velocity from this nozzle. We should remember here this velocity, that is what is contributing our thrust component. Okay. Now, here we have our T9, we have our V9, that is what is giving the information in terms of what will be the exit velocity from the nozzle. Now, very important parameter, that is what is to be known to us, it is what is the bypass ratio of the engine. Maybe when in the initial stage we have information about the bypass ratio, if it is not known to us, we need to calculate that bypass ratio, and that bypass ratio we can calculate if we are correlating our free turbine work with the work, that is what is required to rotate the unducted fan. So, here in this case we can write down this. So, here it says the unducted fan work I can write down as m dot into Cp delta T0, my free turbine work that we can write down as m dot C 1 plus F Cp delta T0. Now, what we know in terms of mass flow rate of unducted fan, that is what we can correlate in terms of beta, that beta is nothing but the bypass ratio. So, based on that we can calculate what will be our beta or bypass ratio of this engine. Okay. Now, once we have all this information, our target is to calculate the performance parameters. So, for this prop fan engine configuration, we have different performance parameter. Very first parameter we can say is what will be the total thrust generated by this engine, and that is what is given by thrust generated by unducted fan plus thrust generated by the core engine. Now, when we say for the fan, then that is what can be written as a beta into m dot core V unducted fan minus V infinity. So, what will be the exit velocity from the unducted fan, that is what we are putting here. Similarly, for the nozzle we can write down in terms of m dot core into 1 plus F, this is V9 of the nozzle minus V infinity. There is one more interesting parameter, that is what has been defined mainly for this prop fan, it is say thrust ratio, and the thrust ratio is a ratio of thrust generated by unducted fan divided by thrust generated by our core engine. Okay, since here our major concern is a free turbine, and this free turbine it is used to generate the power in order to rotate the unducted fan. That is the reason many configuration, many calculation people they are calculating, say researchers they are calculating equivalent power, and that equivalent power it is given by power to be consumed by unducted fan plus the power that is what is been generated by this nozzle, and this nozzle power that is what we say jet nozzle power, it is T into V infinity, and unducted power that is what we can write down in terms of say thrust into velocity. Now, once we have all this information, we need to calculate our other important parameters, which are say propulsive efficiency, thermal efficiency, overall efficiency, thrust specific fuel consumption, and say equivalent specific fuel consumption. So, let us take what will be the formulation for the propulsive efficiency. If we look at propulsive efficiency, as we have discussed, this will be total thrust into V infinity. Let me put the point here. So, the designer will try to design the engine in such a way that the exhaust which is coming out from the free turbine, that also can be utilized in order to generate the thrust. If you recall, similar kind of configuration, similar kind of discussion we were having for say turboprop engine, but when we were discussing about the turboshaft engine, where our whole purpose or sole purpose it is to generate the power only. So, that is the reason why the thrust term, that is what was not coming into the picture. Similarly, here this is what we can write down total thrust into V infinity, and this is representing the kinetic energy both for say our core engine as well as for the bypass kind of configurations. Similarly, we have our next parameter, that is what is say thermal efficiency. This thermal efficiency we can write down by denominator of mf into qr, that is nothing but the calorific value, or we can say it is the amount of heat input what we are putting. Be careful when we are discussing about say engines application for aircraft, we are more interested in thrust. Okay. So, that is the reason why all this formulation, that is what will be coming in terms of thrust. But when we were discussing about the shaft engine, where we were discussing in terms of shaft power. So, do not get confused with this kind of formula here. Now, in terms of overall efficiency, that is what can be written in terms of thermal efficiency into propulsive efficiency. Many times people they are defining the fuel economy in terms of thrust specific fuel consumption, that is what is given by m dot divided by thrust. This thrust we are configuring in terms of say total thrust. And the next parameter what we have is equivalent specific fuel consumption, when we are configuring this engine and considering the shaft power into the picture. So, this can be configured both the way in terms of thrust specific fuel consumption as well as for equivalent specific fuel consumption. So, I am sure this all what we have discussed, the thermal cycle analysis for the prop fan, that is what will be giving you clear idea how the cycle analysis, thermal cycle analysis, that is what is different from what all we have discussed till now. So, based on that you will be configuring or say you will be calculating the performance of the future engines or already existing engines which are having this kind of configuration. Now, in next lecture we will be solving the numerical, that is what will be giving the idea and confidence for solving the thermal cycle analysis for the prop fans. So, here we are stopping with. So, in next lecture let us try to take the actual engine information and let us try to solve that numerical. Thank you very much.